to enable us to use or exploit enzymes in industrial biotechnology, we have to have a basic understanding of how enzymes work. This is something that we're going to cover briefly in Module 2 of this Industrial Biotechnology MOOC. So what we know is that enzymes are biological catalysts that provide an alternative reaction route and can stabilize reaction intermediates for an overall reaction. They're catalysts because they reduce the energy that's required to reach the highest point on the free energy diagram for an overall reaction. And we can see this on the schematic slide here, where the uncatalyzed reaction pathway is shown using the red curve. And in the presence of an enzyme, we can see that the energy required to overcome this hill, if you like, of free energy is reduced, and therefore the overall rate of an enzyme catalyzed reaction is accelerated versus the uncatalyzed reaction. Now, as true for many catalysts, or indeed all catalysts, enzymes themselves are not consumed or permanently altered during the overall reaction, and they do not alter the chemical equilibrium between the reactants and products. Their role is simply to speed up the attainment of that equilibrium and to accelerate the overall transition of reactants going to products. So how do enzymes achieve that? So how do enzymes achieve their function? Well, in the first module we learnt that proteins are inherently very flexible molecules, and this gives rise to the idea of induced fit that we introduced in the first module, or indeed conformational selection, where we can explore different overall structures of the enzyme and to use that intrinsic property as part of the catalytic cycle. Underpinning the fundamental basis of enzyme catalysis is the idea of transition state stabilization. At the top of the free energy hill that we introduced on the previous slide, we have what's called the transition state for the overall reaction, in which we move from the reactant side of the barrier to the product side of the barrier. What enzymes need to do is to reduce the energy of this transition state by stabilizing selectively the energetics of that transition state, and they can do this in a variety of ways. Now, within that common concept, we also have other features of enzyme catalysis that we'll explore on the next slides. We can see that we have catalysis by a principle called bond strain, catalysis by proximity and orientation. We can have acid-base catalysis, where we can supply, through proton donors and acceptors in the enzyme active site, protons at key parts of the catalytic cycle. We can also see evidence for electrostatic catalysis, covalent catalysis, and even in more recent studies of enzyme systems, we have evidence for quantum processes involved in the catalytic cycle through a process called quantum tunneling. So let's take a look at induced fit and conformational change in more detail. We know that enzymes are flexible. They undergo a whole range of molecular and atomic vibrations, rotations of side chains in the overall protein macromolecule, and indeed large domains or sections of the protein sequence undergo major structural change during the catalytic cycle. Some enzymes undergo major structural rearrangements when binding substrates or inhibitors, and a good example here is the enzyme hexokinase, where structural rearrangements are affected after glucose binds into the active site of the protein, and the net result is that this positions reactive residues in the enzyme active site close to the substrate molecule to allow catalysis to proceed. There are many examples in the literature of protein molecules undergoing major structural change as part of the catalytic cycle. The graphic here shows another enzyme, cytochrome P450 reductase, which catalyzes simple hydride and electron transfer reactions between different cofactors, these small organic cofactors that also assist in the reaction. And we can see in this simple two-step process shown in the graphic here, that the enzyme transitions from a more closed structure to an open structure, and that dynamical change is intrinsically linked to the catalytic process in this particular enzyme. So the concept of bond strain is also important in some enzyme catalyzed reactions. So enzyme substrate binding in this case reorients the active site structure, and this can lead to bond strain in the substrate molecule that's bound within the enzyme active site. And this bond strain therefore favors the progression of the substrates from the reactant side of the barrier to the top of the hill or the transition state. A substrate bond is then broken through catalysis, leading to the products, and we therefore fall down then on the product side of the barrier as we release that strain. This is a particular feature of the enzyme family known as the lyases. Lyases are enzymes that catalyze the cleavage of carbon-carbon, carbon-oxygen and carbon-nitrogen bonds by means other than through hydrolysis or oxidation, as observed with many other types of enzyme family. And bond strain is very much a feature of the reaction cycle catalyzed by these enzymes. Proximity and orientation is another important aspect of enzyme catalysis, and as the name suggests, this really just involves the bringing together of substrates in a close environment within the enzyme active site, and therefore positions those substrates in a geometry that is ideal for the catalytic process. So the binding to the enzyme and active site effectively concentrates the substrates in the enzyme active site, and the reaction is now more favored as substrate binding places it in the proximity of catalytically active residues that are present in the protein polypeptide chain. Indeed, we also know that similar reactions will occur faster if the bonds are linked intramolecularly, as shown in the simple scheme on the lower left of this particular slide. Here we have two reaction sequences that are very similar. In one case, the reaction is occurring across two small molecules, an intermolecular reaction, and on the bottom sequence you can see a similar reaction occurring in an intramolecular fashion, and we can see that the rate constants for the intramolecular process are indeed higher than for the intermolecular process, and this is a nice example of how co-location, if you like, of the reacting groups on an enzyme surface can indeed contribute to the overall rate enhancement achieved by the enzyme. Acid-base catalysis is another aspect of enzyme catalysis that's fundamentally important to many enzyme systems. This is a frequently used reaction type. We see it, for example, in the hydrolysis of esters or peptide bonds by proteases and other enzymes. And what the enzymes do in this case is to use proton donors, or general acids, and proton acceptors, general bases, strategically located within the enzyme active site to supply a proton or remove a proton at a key part in the enzyme catalytic sequence. As expected, therefore, the reactions are sensitive to the solution pH, and they may be concerted. A good example is the enzyme triphosphate isomerase, which is located in the main glycolytic pathway of most organisms, and here you can see from this simple graphic that we have movement of protons through acid-base chemistry as we transform the substrate molecule, shown bound here in black in the enzyme active site. Electrostatic catalysis is a key way in which enzymes can effect catalysis by stabilizing electrical charge that might develop in the transition state as we transition from the reactant side to the product side of the barrier. Also, desolvation that we briefly introduced in the first module involves water expulsion from the active site when a substrate binds, and by expelling water from the enzyme active site, we can enhance electrostatic interactions that are already present in the enzyme active site. Expulsion of water can also lead to the protection of reactive groups from bound water in the enzyme active site. So the involvement of charged enzyme functional groups in stabilizing otherwise unstable intermediates is a key part of the catalytic strategy. And again, we can see that, for example, here in the reaction catalyzed by carboxypeptidase, where the tetrahedral intermediate is stabilized by a partial ionic bond formed between the zinc ion and a negative charge on the oxygen that forms during the reaction cycle. Another strategy is covalent catalysis, and in covalent catalysis what we're doing is to form an intermediate state in which the substrate is covalently attached to a nucleophilic group on the enzyme surface. Nucleophilic catalysis exploits the use of strong nucleophilic groups, those groups in the enzyme or the protein molecule which have a stronger nucleophilic properties than water itself, and these typically are residues such as serine, cysteine, aspartate, glutamate, or histidine amino acid side chains in a protein polypeptide sequence, or occasionally the nucleophile can be supplied by a coenzyme or small organic molecule bound in the enzyme active site, such as thiamine or biotin. And again, a good example here is the reaction cycle catalyzed by acetoacetic acid decarboxylase, where we get covalent formation of a so-called enzyme imine intermediate between the substrate molecule and the enzyme molecule, which then allows decarboxylation to occur and release of and breakage of that covalent species through hydrolysis with water can then release the free enzyme and products of the reaction. In electrophilic catalysis, we can exploit bound metal ions, which are often complexed with a substrate in the enzyme active site, and a good example here is the glycolytic enzyme known as enolase that uses bound magnesium ions to effect the activation of a carbon-hydrogen bond such that lysine 3,4,5 here can abstract a proton from that substrate molecule and drive the reaction forward. And then finally, in recent years, we've begun to appreciate that for enzymes that catalyze small particle transfer, that is, for example, electron transfer or hydrogen transfer reactions such as protons or hydrides or H radicals, that in fact we can also exploit quantum tunneling processes. Recall that for enzyme catalyzed reactions, we have to move from a reactant side of the barrier to a product side of the barrier through the top of that barrier known as a transition state. In quantum tunneling processes, we can pass through that barrier by exploiting wave-particle duality, not passing through the classical transition state, but transitioning through that barrier at a lower energetic point on that free energy surface. The distances traveled by quantum tunneling decreases with an increase in mass. So electrons are very effective at tunneling over relatively large distances, up to around about 14 angstroms, and hydrogen can indeed tunnel over much smaller distances, typically around about an angstrom. And these are the typical sort of H transfer distances we see in many enzyme catalytic cycles. The whole process is potentially helped by, again, the inherent flexibility of enzyme molecules, so-called promoting motions that are part of that flexibility, help to manipulate the barrier properties, thereby facilitating the quantum tunneling process. So what we've seen in this module is a variety of catalytic strategies used by enzyme molecules to facilitate the conversion of substrates into products at high reaction rates, primarily based on strategies that are focused on moving from a ground reactant state to a transition state and then to the product side of the barrier, but in some cases, as we've just seen on the last slide, also using quantum tunneling type approaches whereby we can bypass transition through the classical transition state and move directly from the reactant side of the barrier to the product side of the barrier by quantum mechanical tunneling.